Differentials. Okay, so as I said at the beginning of this section, this is the perfect time to introduce this idea, although the idea of differentials is much more far-reaching than what we're going to see in this section. Okay, so differentials. So let's see. So I've drawn a curve f of x, okay, and I have identified a point down here, and I've attempted to draw, to the best of my ability, a tangent line right there. So what's this idea of differentials? Here's what we're going to do. I'm going to draw a triangle extending out this way for maybe about that far. I think that'll work. Okay. And then I'm going to draw it straight up. And I'm not going to stop at the tangent line. I'm actually going to go all the way to the function. Okay. And that's a little right triangle. All right, what's going on here? The differentials, there's here, if we think of x and y as our variables, then each x and y have a differential. Okay. I'm going to call this horizontal distance here the differential of x. And it's notated dx, the differential of x. All right. And I'm going to label this portion up to the tangent line as the differential of y, notated dy. And then we can tell it has to go a little bit further to reach the actual function value. Okay. Now let's take a look at this. Let's step back for a second. When we draw that triangle, aren't we drawing a rise and a run? Right? From this location to this location, we've got the rise dy and the run dx. And doesn't rise over run describe the slope of the tangent line? Okay, so I'm going to write this right here. Some of this notation obviously looks familiar. Okay. So dy is the rise, dx is the run, rise over run. Well, that's equal to the slope of the tangent line, which we refer, if that's f of x, we refer to as f prime of x. Oh, so differentials is where that Leibniz notation comes from, dy over dx. Okay, but there's a significant conceptual shift that we have just seen. Yes, dy over dx also means the derivative or the slope of the tangent line. But when we think of it as a rise over a run, we are thinking of these as individual values. We're no longer thinking of it just as one whole object like we do f prime of x. We're thinking of this is a value divided by this other value. We are thinking of it like a fraction. Okay, so if it's a fraction, then we can multiply the dx over to this side. And here's what we're going to write. dy equals f prime of x dx, right? We just multiply that over like it was any other number. That's the differential of y. That's the differential of x. And we can see how they are related to one another. Well, what is this vertical length? Well, it's the derivative multiplied by that horizontal length. The differential of y and how it's connected to the differential of x. Okay, now maybe some of you are thinking here, what is going on? Because you've been saying, like speaking to me, like I've been saying that dy over dx is not a fraction. Although it kind of behaves like a fraction sometimes. When it comes to the units of derivatives, we can look at it and get the unit over the unit. If you remember the stuff with the chain rule and how, if you remember that with like du over dx and dy over du, then thinking of it like a fraction is helpful. Okay, so the thing is, it is a fraction, but it depends on how you're thinking of it at the time. So I really didn't lie to you when I said it's not a fraction, because at that time we were not thinking of it as a fraction. We were thinking of it like a new function. But if you go deeper into the concept, and if you think about it like a differential instead of a derivative, then yes, it's numerator and denominator, and we can multiply that over. And these are two separate values. Wow. Okay, depends on how you think of it. I didn't really lie to you. All right. I didn't want to overwhelm you with all this back then. Like there was no need for that. Okay. Okay, so what we're going to do is we're just going to explore this idea of differentials, and then we're going to see how they're connected to approximations, linear approximations, okay? Let's just explore this new idea of differentials for a second. So I've got these two examples down here. I'm just going to keep this, and I'm just going to show you all this at once. Obviously we'll talk through it. So it really comes down to this new formula that we've seen, the differential formula, if you will. Okay, so let's say we were told y equals x to the 2/3. And we wanted to know the relationship between the differentials. Okay, well, if y equals 2/3, then what we're going to do is not take the derivative of both sides. We're going to take the differential of both sides. Take the differential of both sides. So the differential of y is dy. Simple as that. The differential over here, well, we follow the formula. We take the derivative as normal, 2/3 x to the negative 1/3, and then we multiply by the differential of x. And there's really a feel of like that implicit differentiation going on, right? Take the derivative as normal, but then multiply it by the differential of x. Kind of like before you might say like dx over dt or something. That's not what we're doing. It's the differential, not a derivative. Very, very subtle difference. Okay. And you can even see like, oh, well, if we divided this back over, I mean, dy over dx would equal that. Yeah, and that would be a derivative. But when we multiply it, we're thinking of it as a differential. One more example, and I think you get it here, but just in case there's any confusion, let's look at this one also. How about y equals t plus 1 over 2t minus 1? What if we were to take the differential of both sides? Okay, so the differential of y, of course, is just the dy. On the right side, though, we take the derivative as we typically would. That needs a quotient rule. So I don't think we need to go through it piece by piece, but all right, low d high minus high d low all over low squared. And then on the end, that derivative gets multiplied by the differential of t, dt. And there's the differential of the right side. Now in this case, that numerator cleans up really well. T's cancel out. We end up with -3. So why not give you the simplified version as well, since it cleans up so well. Differential of y would equal -3 over quantity 2t minus 1 squared times the differential of t, dt. Okay. I think I'm actually going to pause this video, stop this video here. We'll connect this to linear approximations next.